Then do a couple more problems from chapter 4 or exam 4. Identify the diatomic element whose root mean square velocity is most likely to be 217.723 meters per second at a temperature of 25.00 degrees Celsius. So this is the equation that you're going to use with the root mean square velocity. So the RMS after the mu is equal to the square root of 3RT over the molar mass. And you rearrange that, you can solve for the molar mass, and then once you get that molar mass, since it's diatomic, you can divide it by 2 and hopefully pick a diatomic element whose periodic table mass is close to that. So start off here. You have 3, and the R value that I gave you was, and now of course remember that comes out in kilograms per mole, so everything's going to cancel out except the kilograms over the moles. So you multiply straight across, divide by the bottom, and you'll get kilograms per mole, which you need to convert by multiplying by 1,000, and you get 156.89 for that, and then, or approximately that, and you divide it by 2, and you get it says 78 point something, which of your diatomic elements, average atomic mass, it's closest to the element bromine for that one. Here you have a problem where you had to determine the mass in milligrams of nitrogen gas occupying a volume of 300 milliliters at 125.55 degrees Celsius and a pressure of 21.25 psi. And then round your answer to 2 decimal places at the end of the calculation. So here I did this one the way I alluded to earlier, where I'm solving for N, because ultimately I could get to mass of nitrogen, but I don't have a way to do that without first getting to moles of nitrogen. But once I get to moles, I can convert to grams of N2, and then I can convert from grams to milligrams. So I substituted all my pressures here. I converted my milliliters to liters because I'm going to use a R value here, an R value that's 1.20591 from my reference material, which that's the one for liters psi per mole Kelvin. And now convert my Celsius temperature to Kelvin. So when I do that work, I'll get N number of moles of nitrogen. Once I'm in moles of nitrogen, I can use my molar mass from the periodic table. Since it's diatomic, multiply it by 2, and I get 28.0134, and that cancels out my moles of nitrogen. I'm in grams, so then 1 milligram is 10 to the minus 3 grams, so I'll get out of grams into milligrams, and that should allow me to get to an answer around to 2 decimal places, 371.44 milligrams of N2. Then here we have a problem. I believe in both classes I was asked to work this problem on Wednesday when I came in for a check-in and for any, maybe if y'all needed any review. And I said I would rework or go back over this problem again, or one like it. You have a temperature in degrees Celsius, which you probably already realize it's probably going to have to be converted to Kelvin. You have these masses of these 3 noble gases, and you have this volume of a 12-liter container. And you're supposed to calculate the partial pressure in the unit that I'm requesting, assuming ideal conditions, so that means you can use the ideal gas law. And then tell me the total pressure inside the container in units of pounds per square inch, or psi. So for each one of these, you need to first set them up and determine the number of moles because to get the pressure using the ideal gas law, you multiply nRT and divide by volume. So here I set these up based on what was given in the problem above, the question, and the .982 use the mass of helium to convert it to moles, so that will cancel, and then the grams of neon to convert that to moles using the molar mass, and then the grams of argon using its molar mass to convert to moles. Then I substituted each one of those into this equation. So say the pressure of helium would be equivalent to N, whatever I get for this little step, times R times T, which is the same all the time. The temperature is the same, and the volume is the same. So those two parts stay the same. The N and R change. The R changes because the pressure, requested pressure unit, changes. So I use a different value for R when I calculate those. And then what I did for each one, when I calculated them, I calculated the pressure for helium, partial pressure for helium, and that ended up being 0.467 atmospheres, and then convert that to PSI. Now the chart that you used for, or that I used for this, was the one from the back cover of your textbook, where it had the equivalencies of standard pressure, knowing that 1 atmosphere was standard pressure, and that was equivalent to 14.70 psi. I was able to make this conversion from atmospheres and go ahead and get its equivalence in psi, because I know later I have to do total pressure in psi. So I went ahead and just calculated it to save myself time. And then here I got the answer in millimeters of mercury for neon, because that's what it asked for. And then I went right ahead and converted that to psi using the 760 millimeters of mercury equivalent to 14.70 psi. And then argon, I had 4 sig figs when I did my argon, so this was my pressure in bar units, bar from up above here. And then I went ahead and just converted that to psi, because the last step I had to add them up and report them to 2 decimal places, because that has 2, that has 3, that has 2. So my final answer had to be changed to reflect that, only 2 decimal places. So my total pressure was 35.50 psi, and these are my individual partial pressures in the units that were requested. So that gives you a few examples of problems that you can work on from exam 4, and hopefully you'll practice those as well, and have a good luck on your final.